later, I just get 1.079, something like that. But if you don't have a log key, then you'll have to do this. Natural log 12 over, careful, natural log, what's the base if it's not there, right? It's 10. See, you have to recognize that here, that this is actually log base 10 of 12. You have to remember that. And then you type that into your calculator. And you should get approximately 1.079. Now, what's this one? You just hit it on your calculator, right? Just do it on your calculator. However, check this out. I just want to show you that the formula would still work. If I use a formula, what's the base down here? What's the base of the natural log? E, right? So I would have to type into my calculator natural log of 12 over natural log of what? E. Now, you see this natural log of E? Imagine that that's natural log of E to the first power, all right? And then go back to property
5.
No. Property 3? Is it 3 or 2? I don't remember which. I think it's 2. Look at property 2. What did property 2 say? Look at the one we did the special case of property 2. What was the special case with the natural log? I said natural log of e to the x is x. And do you all see this is natural log of e to the 1? So the x is 1. What's our answer on the bottom? 1. Do y'all see that this is just natural log of 12 over 1, which is just natural log of 12, damn it, right? That's all it is. Jeez. What do you think? Everything good? Any questions? Y'all feel uncomfortable with this at all? All right. Just oh, you like these on the test? Okay. All right. 6.5 is done. All right. Properties of logs. Properties of logs is over. Now we're going to have to use these properties to do the next section, which is called solving logarithmic and exponential equations.
Are we going to do exponential growth and decay more?
Yes, we will talk about exponential growth and decay and word problem stuff. We'll get to that after we finish the test. So next week. It won't be on, you know what, I think it's on your review.
Yeah.
We might talk about it next class, but just one example of it. Just one particular example. All right, you ready?
Yep.
All of this development of logarithms, one of the main ideas was so that we could solve some equations. All right? So I want to take you back real quick. I want to take you back to an equation that we can't solve. All right? Something like this. If I write 2 to the x equals 8, well, let's start with that one. We know the answer to this, don't we? We can just look at it. The answer is 3, right? 2 cubed is 8. So this is boring, right? Because we can do this. Boring. The answer is 3. But what about 2 to the x equals 7? Well, we actually just did that, didn't we? Didn't we do a problem a second ago where we said 2 to what power is 7? So we're going to take that and we're going to convert this into, right now it's in exponential form. We're going to convert it to the log form. So convert this to log form. That means you're going to write a log. What's the base going to be? The base will always be the base over here, 2. And then think about the loop. So 7 goes here, and what goes here? X. Now, do you see I can solve for x now? As long as I can figure out the left-hand side. But how do you do the left-hand side? The change of base formula we just learned, right? So this is just natural log 7 over natural log 2, and that's x, and I think we got, I don't know, 2 point something, right? 2.807, approximately x. And we're done. We have a way of solving an equation like that now. Do you see that? We have a way of doing it. And so what we'll do now is we'll try and do some harder and harder ones. All right? We're going to try and do some harder and harder equations. So the next one I'd like us to do, I'm just going to pick some out of here. Let's go with 50. So we're right now, just so you know what we're doing, we are solving exponential equations. That's what we're doing right now. That was an equation, right, involving our variable being in the exponent. So the next one is 2 to the negative x equals 1.5. So when I look at that, the first thing I have to recognize is that this is an exponential equation because the variable's up in the exponent, right? Variable's in the exponent, it's an exponential equation. So I'm going to try and convert this to log form first. So I write log, what's my base? 2, think about the loop. 1.5 goes here. And what goes here? Careful. Negative x. Negative x goes there. Not x, negative x, right? Now, the left-hand side you can do on your calculator, can't you? You get your calculator, you can do natural log of 1.5 over natural log of 2, and that will be equal to negative x. Get your calculator out, figure out the left-hand side. Natural log 1.5 divided by natural log 2. I get a decimal about 0.585. Y'all okay with that? 0.585 is equal to negative x. I don't want negative x, I want x, right? So multiply both sides by -1, and that'll give you negative 0.585 is x, approximately x. There you go. Was that pretty straightforward? Just do the logarithmic form, and then use your calculator, solve for x. Of course, these are going to get harder, right? Oh, yeah, I like this one. 2 to the x plus 1. Please pay attention to this one. 5 to the 1 minus 2x. Oh, here, now we got something interesting. We've got something very interesting. I want to know what x is. The difference between that one and this one is that for here, when we went to the loop, when we rewrote this log and did the loop, everything over here worked out great, didn't it? Calculator, everything was beautiful. Yeah? Okay, so here's what I'm going to do. I'm going to convert this to a log, right? I'm going to convert this to a log. When I convert this to log form, I'm going to write log. Now, this is the part I think is tricky. What base do I use, the 2 or the 5? It's up to you. It's actually up to you. It depends on how you want to look at it. I'm going to look at it with the 2, all right? So I'm going to do the 2 here, and now I'm going to think about the loop. Pay attention to the loop. The loop says we're supposed to take 2 and raise it to what power? So what's the power on the 2 over there? X plus 1. And what must that equal? That whole thing right there, right? That whole thing. 5 to the 1 minus 2x. Let's just make sure you understand that. If I do the loop here, take 2 and raise it to this, will that be equal to that? Is that what the original equation was? Yes? 2 raised to this equals that whole thing. Yeah? So everyone is okay with that notation? The question is, what the hell do you do now? Because remember when we did that loop over here? We got this and we could go straight to our calculators? Because there weren't any x's over here anymore, were there? Do you see we have x's over here still? Okay, so let me write down where we are. We have log base 2 of 5 raised to the 1 minus 2x equals x plus 1. All right, that's where we are. Drum roll. Raise your hand if you know what to do next. Raise your hand if you feel like you know what to do. I want to see if anyone sees it. You think you know? Okay, hold on. You think you know? Think so? And give everyone a chance to come up with some idea here. Remember, the idea is that we're trying to get x not to be in an exponent anymore, right? And like over here, the x was up here, but when we redid it, rewrote as a log with the loop, the x kind of disappeared from the exponent, became down, like down in the base, right? Like downstairs. And then we solved that on our calculator. Here, we did this sort of loop, rewrite it, but we still have an x up here. Okay, so raise your hand if you think you know. Okay. Who's not sure? Who's not sure? Not sure? Okay, then we'll go with you. All right, you ready? All right, so I'm trying, this is a problem right here. Do you see why I can't use a calculator here? Do you agree if it was just a 5, I could use my calculator? Yes? Okay, so we've got something up here that we don't want up here, right? So how can we get it out of here? Well, do you see we have a logarithm of something to a power? Don't we have a property that allows us to pull powers out front? Property 6, right? Property 6. Property 6 allows me to take this and slap it out front, doesn't it? That is a property of logarithms. And won't that get the x out of the exponent? So that's what I'm going to do. Weird, right? Kind of a little hidden there. So let me pull that out. Now when I pull it out front, I have to write 1 minus 2x in parentheses, because that's the whole thing. Next to it, I'm multiplying log base 2 of 5 equals x plus 1. So what I did there was property 6. Y'all still okay? Now check this out. Can we do that now? We can. That we can do on our calculator. That's natural log of 5 divided by natural log of 2. So somebody do that for me. What's natural log 5 divided by natural log 2, natural log 5 over natural log 2. What do you get? About 2.321. We okay with that, everyone? 3.231 equals x, you round to 2? It's okay. Look, I don't really care. We're not building bridges yet, right? So we'll be all right with that. You see what you have? What type of equation is this? There's a name for this type of equation. You have one variable in there, x's and numbers, right? Linear. This is a linear equation, isn't it? It's just a linear equation. Solve for x. So I'm going to distribute this through. What's 2.31 times, what's 2.321 times 1? 2.321. Minus, okay, what's 2.321 times 2x? Well, we have to double that on our calculator, right? 2.3, so what is it? 4.642? Is that right? 4.642x? Yeah? Oh, so you've got different rounding. That's okay. That's okay. Yeah, don't worry about it if you rounded that. Just, I think if we're all within the first 2 decimal places, we're okay. Equals x plus 1. All right. I did that to remove the parentheses, didn't I? And now I just need to get x on one side and numbers on the other. So what I think I'll do is I'll add this to both sides. This is like a 1x. I'm going to add this to both sides, and I'm going to subtract 1 on both sides. So I'm adding 4 plus 642x, adding 4.642x. I'm subtracting 1 here and subtracting 1 there. I'm out of room. Let's see what I've got. What's my left-hand side? 1.321 equals my right-hand side, 5.642x. These went away, those went away. And then those two together gave me the 1.321. And then when I added these together, I just added the 1 and the 4.642 together, give me 5.642. Last step, divide both sides by 5.642. So you get x is approximately, what'd you get? 0.234. Good enough. What do y'all think of that? It's a little bit different than that first example, right? I mean, the first example is just straight away, you go to the loop and you're done, use the formula. Here, we did the loop, but then we had to use a property of logs to pull that thing out and then solve the equation. Now, I'd like to check our answer. I'm just curious that this works. So if I were to take this original equation and replace x with 0.234, this should be true. So imagine replacing that with 0.234. I get 2 to the 0.234 plus 1 would be 1.234. Does that equal 5 raised to the, okay, I need to do this on my calculator. I need to do 1 minus, so on my calculator, I'm going to do 1 minus 2 times x. X was 0.234. That comes out to be 0.532. So if I take 2 and I raise it to the 1.234, is that approximately equal to 5 raised to that? So I check it. 2 raised to the 1.234. On the left-hand side, when I do this, I get 2.352. And when I do this on my calculator, 5 raised to the 0.532, I get 2.354. I get 4 here. So I'm off a little bit. Why? Because I was rounding throughout the problem. So I'm going to have rounding error. But I mean, I feel pretty good about it, right? They're pretty close to one another. Plus or minus. We're within what? These are tenths, hundredths. This is thousandths. I'm within 2 thousandths. You know, again, depends on what you're doing with it, right? How are we doing time-wise? We're all right? Let's look at another one. Ooh, 59 looks fun. But we need to do something like 62. Let's do one like 62. 3 to the 2x plus 3 to the x minus 2 equals 0. So put a star next to this. This is a classic problem, meaning college algebra students see this and they need to see it, and it's going to be on a test for sure. If you've looked at the review, there's a problem like this on the review. All right. So if you go and you look at what we've done before, we were able to do the loop, weren't we? And the reason we were able to do the loop is because we had something to the x on one side of the equation, and then we rewrote it as log. But here we have, do you see we have two things being added together, and they're both being raised to something with x's in them, and then we also have a minus 2? This is a special form that we have to recognize something here, right? And it's not very natural the first time you see it to actually recognize this, so I'm going to force you to see it, all right? Please see that this is the same as this. Do you all agree that 3 to the 2x is the same as 3 to the x squared? Because if you take something to a power, what do you do with these powers? Multiply. What's 2 times x? 2x. So do you all agree that's the same? So that's the same equation, isn't it? Now I'd like for you to squint your eyes and make a substitution. I'm going to pick a letter here. I'm going to let m be equal to 3 to the x. I have a 3 to the x here. I have a 3 to the x here, don't I? So this is 3 to the x squared. This is just 3 to the x by itself. If I replace the 3 to the x with m, what does this become? M what? M squared plus m minus 2, and that's a quadratic equation, isn't it? This is a quadratic equation now. You probably weren't expecting that. And how do we solve quadratic equations? We either factor them or we use a quadratic formula, right? Now, I'm going to expect that you could do that and get solutions here. I'm going to factor it. Hopefully it does. Let's see. M,
2 minus 1.
2, positive 2,
Yeah.
and minus 1. That's the factorization of that, which means we set each of these equal to 0. We get 2 solutions, negative 2 and positive 1, right? Those are our 2 answers. Well, those are the 2 solutions for m, aren't they? But we're not trying to solve for m, we're trying to solve for x. Do I have any questions up to this point? I looked at this, I said, this is different than what we've done before. Oh, I see what they're doing. That's a squared. I'm going to make a substitution. It's quadratic. I factor. I set it equals 0. I get 2 solutions. Now I go back and I replace m with what? Here and here, I'm going to replace them with what? 3 to the x. So I'm going to continue. So I have 3 to the x equals negative 2, and the other one is 3 to the x equals 1. Right? This is m. M equals negative 2. And then m equals 1. I think we can solve these without a calculator. You could use the log here, okay? You could use the log, but I think we can solve this one just by looking. 3 to what power is 1? 0. Now, if you didn't like that, what you would do is you would rewrite this as log base 3 of 1 equals x. Check the loop here. 3 to the x equals 1. 3 to the x equals 1, right? But what happens when you plug a log in? I'm sorry, a log. What happens if you plug a 1 into any log? That was the very first property. You get 0, right? So that's why our answer here is 0. Now, on this one, we could do the loop as well, couldn't we? We could do the log and loop. But I want you to think about this. 3 to the x is an exponential function, isn't it? Like if you graphed it, 3 to the x, it would be growth or decay? It'd be growth, right? Can that graph ever be negative 2? Think about what the graph. Remember, it never went below the x-axis, which means this is not possible. So we should get no solution here. But let's just check it with the loop. If I did the loop, it would look like this. Log 3, over here I'd have x, and here would be negative 2. And do you see you have a domain problem? You can't plug a negative 2 in. Try it on your calculator if you're not convinced. Try to use your change of base formula and try and type that into your calculator. Try and take natural log of negative 2, and it's going to tell you not real answer, or it's going to say error or something like that. That means that there's no solution to this. Okay? There's no solution, no real solution. You don't have to say real. No real solution. Just say no solution. So we only have one answer. The answer is 0. You could, yeah, there are possibly imaginary number solutions, but I want to do one more of those, and then we're going to call it a day. So for the next one, it's going to be very similar to the one we just did. I'm going to do, which one do I want? Let's do number 70. 2 times 49 to the x plus 11 times 7 to the x plus 5 equals 0. The instructions here are to solve for x. So when you see a problem like this, right, in your homework or on a test, the fact that there are 3 terms, y'all see there's 3 terms? 1, 2, 3 equals 0. You should be thinking maybe this is quadratic. Maybe it's quadratic. But if I do that, I'm going to have to replace something, right? Like we just did in the previous problem, we said let m be 3 to the x. Here, I want to replace something here.
7x.
7 to the x.
Because then you can square it side out.
So this right here, you thinking that should be m?
Yeah.
That needs to be a 7 to the x also, though. So let's look at 49 to the x for a second. Let's see, how could I rewrite that as a 7 to the x somehow? Yeah, this is the same as 7 squared to the x, isn't it? Because 49 is 7 squared. But then that's just 7 to what power? 2x. 2x. You multiply the two powers. 2 times x. So 7 to the 2x is the same as 49 to the x. So I'm going to rewrite this as 2 times 7 to the 2x plus 11 times 7 to the x plus 5 equals 0. You know what some students do? Y'all can tell me if this is right or wrong. Some students will multiply these two together and get 98 to the x, and then they'll get 77 to the x. Is that right? Can I multiply the 2 and the 49 together right now? Why not?
Variable.
Why?
The variable.
Yeah, the variable. I don't know what the variable is, right? Order of operations says you must always do what before what? Exponents before you do multiplication. And if I don't know what that exponent is, then I can't tell you, I can't multiply those together, right? I can't. You can even check it using something else like this. If you do 2 times 3 to the third power, what would that mean? 2 times what? 27? And what's 2 times 27? 54, right? Is that the same answer you would have got if you would have done 2 times 3 and got 6 cubed? Well, 6 cubed is not 54, okay? So which is correct? This is correct, because you must do this first, then the multiplication. You can't do the multiplication first, then the exponent. So that's why I did not multiply these together, all right? That's why. Now, maybe one more thing to help us see this. This is 2 times, this is 7 to the x squared plus 11 times 7 to the x plus 5 equals 0. That's just to help us see that this 7 to the 2x really means 7 to the x squared. I'm going to replace all my 7 to the x's with what? You want to use m again? Let's let m be 7 to the x. So we have 2m squared plus 11m plus 5 equals 0. We try and factor. Let's see, we get 2m here, m here, 5 here, 1 here. And double check. 2m squared, 10m, and then 1m, that's 11m, and then 1 times 5. So that works. Oh, shit. Am I going to have no solution here? Maybe, maybe not. Let's see. So set those each equal to 0. 2m plus 1 equals 0. And the other one is m plus 5 equals 0. My two solutions are m equals negative 1/2 and m equals negative 5. And then what's m? Did I write the problem down right? Yeah, I did. What's m? M is 7 to the x. So 7 to the x is negative 1/2. And then 7 to the x is negative 5. What can you tell me about both of those? There should be no solutions, right, to either one of those. Can you raise 7 to any power and get a negative? Think about the graph again. No. Here? No. So we have no solution at all for this equation. This equation has no solution. Okay, what I'd like for you to do is, for homework, do your 6.5 homework. try what's there. Okay, that's a lot of work right there. And then if you want to do the 6.6, only for 6.6, I would only look at problems 45 through 71. You know, start with the odds. See how that goes for you, all right? Don't do anything else for 6.6. We're going to do a few more, next class we're going to do a few more of these exponential equations. Then we're going to do log equations. We haven't even touched log equations yet. And then we will do some word problems and talk about the test. All right, everyone, have a great rest of your day.